Welcome to the 12th and final week of this open course on diffusion in multi-component solids. In this lecture, I will introduce you to the short circuit diffusion paths or fast diffusion paths. So, what are these short circuit diffusion paths? So far, most of the discussion focused on crystalline solids, in which the atoms are perfectly ordered except for some point defects like vacancies or interstitials. However, in certain one dimensional or two dimensional defects inside these crystalline solids, there is a disarrangement of atoms. Because of this unordered structure in and around these defects, the activation energy for diffusion in this region comes down, and hence these defects are characterized by fast diffusivities. That is why they are referred to as fast diffusivity paths, or in other words they are also referred to as short circuit diffusion paths. Some examples of such fast diffusivity paths are surfaces, grain boundaries, triple junctions and dislocations. So, let us see one by one how these diffusion paths are fast diffusion paths because of the atomic disarrangements. So, let us first consider surfaces. We know that the atoms on top of the surfaces have some unsatisfied bonds. They are also referred to as dangling bonds. For example, let us consider a 1-1-1 surface of an FCC lattice. We know FCC has a coordination number of 12, which means each atom is surrounded by 12 nearest neighboring atoms. So, on 1-1-1 plane specifically, 6 of these 12 neighboring atoms are in plane. So, I have shown an example here. So, the red atom here is an atom that we are talking about, and there are 6 blue atoms shown, which are the in plane neighbors of this red atom. 3 atoms are on top of this plane and 3 more at the bottom of this plane, which are nearest neighbor of these red atoms. Now, suppose if this plane marked by these blue atoms is a surface, which means for this red atom, for example, the 3 top bonds are missing, and this shows us that each atom on a 1-1-1 surface of FCC is characterized by 3 dangling bonds. So, I have shown schematically it here. Now, if there happens to be a surface edge or jog, then obviously there will be more dangling bonds near this surface tape or jog, which is shown here. Because of this very high atomic disorder on the surface, the activation barrier for diffusion or the activation barrier for atomic jumps is very low, and hence the surfaces are characterized by very fast diffusion. That is why we say the surface diffusion is very fast, much faster than the lattice diffusion. Similarly, the next fast diffusion path is grain boundary. We know grain boundary is the interface between 2 adjacent crystals of the same phase. So, I have shown, for example, grain 1 in blue here and grain 2 in red here schematically, and where they meet we can see their lattice positions do not exactly coincide, the lattice positions of grain 1 and grain 2, which means there is an atomic disorder in the plane where they meet, and even in a region near to this meeting plane, that is the grain boundary. and because of this the activation energy for diffusion along the grain boundary is very low, and hence the diffusion is faster along the grain boundary. So, if we look at the plane of the grain boundary, it will look something like this schematically. We can see there are atoms randomly arranged. So, there is no order, there is a atomic disorder, and because of which the diffusivity is faster along the grain boundaries. Similarly, where 3 grain boundaries meet, I have shown schematically here grain boundary 1, GB1, GB2 and GB3. These 3 boundaries will meet in a line, and this line is called triple junction. The triple junction is associated with even more atomic disorder as compared to the grain boundary, and hence the diffusion along triple junction is faster than the diffusion along grain boundaries. Similarly, dislocation is also characterized by some atomic disorder in and around its core. So, I have shown a schematic edge dislocation here. So, we can see the extra half plane here, and the dislocation line is going inside the plane of this screen. There is also a stress field around this dislocation core, and because of this there is a slight atomic disorder in and around the dislocation core, and hence again the diffusion along dislocation is faster than that in the lattice. Obviously, the disorder, the atomic disorder near a dislocation is much lower compared to that in the grain boundary, and hence obviously the diffusion along dislocation is slower than that along grain boundary, but it is faster than the lattice diffusion. Now, the question is, why are these fast diffusivity paths called short circuit diffusion paths? So, let us see it here. Atomic disorder causes enhancement of diffusivity within and around surfaces, grain boundaries, triple junctions and dislocations. Hence, atoms will diffuse faster along these defects. Thus, these defects can transport the atoms to a place within the lattice where they would not reach in presence of only lattice diffusion, which is slow. Let us consider an example here. So, suppose we are considering material A with the grain boundaries of which are shown here, and on top of the surface of A there is a material B which is deposited, and let us allow B to diffuse into A. What happens? If the grain boundary diffusion and lattice diffusion are same, or if the diffusivities along grain boundary and lattice are same, then after a certain time t, the solute or diffusant would have travelled an average distance which is proportional to root dt, and I have shown here by the shaded area, and we can see through both grain and grain boundary the diffusion distance travelled is same, because we are assuming that the diffusivities are same. What happens if the grain boundary diffusion is faster, which is the reality? So, let us consider this example again here. Atom B is diffusing inside this A. If the grain boundary diffusion is faster, which is the case in reality, then the diffusion along the lattice is still same, that is root dt is the distance root dt, but since the grain boundary diffusion is faster, the diffusion penetration along the grain boundary would be much deeper than root dt, and hence we would see that the grain boundaries would be decorated with the solute or the diffusant to a depth which is much deeper than the distance root dt. D is the lattice diffusivity here. Not only that, but from this grain boundary the solute will now leak into the lattice grains, and thus we can see, because of the fast diffusivity along the grain boundaries, the solute has reached to a point inside the lattice, for example the one I have shown here, to which the diffusion would not reach in absence of these grain boundaries. If only lattice diffusion was active, obviously this distance from surface is much larger than the distance root dt, and hence in absence of grain boundaries the diffusion would not have penetrated to this point. But now because of the grain boundaries, this point sees this diffusion here. Thus, by short circuiting via grain boundaries, solute B has reached to a deeper located grain where it would not diffuse by only lattice diffusion, and that is why these paths are called short circuit diffusion paths. You will also note that the diffusion of B here is no longer unidirectional. Although we started with a geometry which looked like there would be a unidirectional diffusion from top to bottom, but because of the presence of grain boundaries and the subsequent leakage from the grain boundary into the lattice, the diffusion is no more one dimensional, it is a 3-dimensional diffusion. So, when we consider grain boundaries also, the problem would become 3-dimensional diffusion. We can similarly consider diffusion along dislocation. I have schematically shown a dislocation line here inside a crystal. One can imagine a small pipe surrounding this dislocation line, and we can imagine the diffusion current to be flowing through this pipe much faster than through the lattice. From this pipe, the diffusion would then spread radially into the lattice, causing a short circuit diffusion path. Because of this pipe analogy which is usually given, diffusion along dislocation is also referred to as pipe diffusion. Now, let us see how these diffusivities along different diffusion paths are relatively placed. The diffusivity will still follow the Arrhenius equation, whether it is through lattice or pipe or grain boundary or surface. So, in lattice, for example, if Q is the activation energy and D0 is the frequency factor, we can write D equal to D0 exponential minus Q by RT. Similarly, for pipe diffusion, QP is the activation energy, QB is the activation energy for grain boundary diffusion, and Qs is the activation energy for surface diffusion. If we plot diffusivity through these different diffusion paths against the inverse of temperature, which I have shown here schematically, we will get 4 lines corresponding to the 4 paths that I have mentioned: ds, db, dp and d. Obviously, the slope of each line would give the activation energy for diffusion along that particular diffusion path. We can see at any temperature the surface diffusivity is the highest, which is followed by grain boundary diffusivity and pipe diffusivity, and the lattice diffusivity is the lowest. If you compare at lower temperature, that is towards the right of this 1 by T scale, we can see the difference between the lower diffusivity and the higher diffusivity is much higher compared to the higher temperature, and that is why we say that the fast diffusivity paths are more dominant at lower temperatures. This we have seen qualitatively. Now, let us try to see when the fast diffusivity path can become dominant. So, for that let us try to see the simple model as proposed by Hart, that is the effective diffusivity model. For that, let us consider a grain boundary of width delta I have shown the grain boundary by this blue box here, and it is in contact with a square shaped grain. The edge length of the square grain is d, which is shown here, and let us say we are considering a unidirectional diffusion along x axis, that is from left to right. And for simplicity, let us assume that the concentration gradient is same inside grain boundary as well as inside grain. So, the diffusion flux along the grain would be given by JL is equal to minus d dou c by dou x. D is the lattice diffusivity, and the flux along grain boundary would be given by JB is equal to minus dB dou c by dou x. dB is the grain boundary diffusivity here, and one can see, since the grain boundary diffusivity is higher than lattice diffusivity, the flux itself would be higher along grain boundary as compared to along the grain. However, we also need to consider the total cross section in order to estimate the total amount of material carried by a particular path, that is grain boundary or grain. So, the total amount of solute diffusing per unit time would be given by JL time cross sectional area of grain plus JB time cross sectional area of grain boundary. The cross sectional area of grain here is, it is a square grain, so it will be d square, and the cross sectional area of grain boundary would be delta times d. And so, the total cross sectional area combining the grain boundary and grain would be d times d plus delta. And if we express the net flux as J is equal to minus d effective times dou c by dou x, the d effective would come out to be this expression here, d times d plus d by delta plus dB times delta by d plus delta. Now, if we consider the volume fraction of sites inside grain boundary, that would be the volume of grain boundary divided by the volume of the grain. The volume of grain boundary is d square delta, and volume of grain is d square times d plus delta, and so the volume fraction of sites inside grain boundary is F is equal to delta over d plus delta. Similarly, the volume fraction of sites inside grain would be 1 minus F, which comes out to be d over d plus delta, and hence the effective diffusion coefficient can be expressed as d effective is equal to F times dB plus 1 minus F times d. This is known as Hart's equation. So, Hart's equation gives the effective diffusivity, which is contributed by the grain boundary diffusivity as well as the lattice diffusivity, but we also need to consider the fraction of sites residing in grain boundary as well as in the grain. Unless the grain size is very small in few nanometers, the fraction F is much smaller, and hence 1 minus F is approximately equal to 1, and we can approximately say d effective is equal to F times dB plus d. Now, let us try to estimate when the contribution from dB may become important. The contribution from dB to d effective may become important. Typically, the grain boundary width is around 0.5 nanometer, and the grain size, even if it is very small grain size, will be, let us say, 5 micron, and F is approximately delta by d, and so we will get F to be approximately 10 to power minus 4, even when we are considering a fine grained material. The grain size is around 5 micron. Now, for the grain boundary diffusion to be significant, let us say the diffusion is significant when the contribution is at least 10% from dB to d effective. So, for this to happen, dB has to be at least 10 to power 3 times the value of d. This is the case when we are considering a fine grained material. For a large grain material, this is going to be even a higher number. Now, this will help to understand why the grain boundary diffusion becomes more dominant at low temperature, because we have seen at low temperature the difference between the grain boundary diffusivity and lattice diffusivity is much higher. So, the grain boundary diffusivity would be much higher than 10,000 times the lattice diffusivity, and hence the grain boundary diffusion will dominate. So, in this case the small value of f will be more than compensated by large value of dB compared to D, and hence D effective will be dominated by the grain boundary diffusivity. At higher temperature, however, the difference becomes smaller and smaller, and when the difference is very small, the fraction f, since fraction f is very small, the contribution from f times dB to D effective will be very small, and hence at higher temperature we say the effect of grain boundary diffusion will be negligible, and this is the reason why we say the grain boundary diffusion will dominate at lower temperature. Also, we can see if the fraction f increases, the grain boundary diffusion term will dominate, but for this fraction f to be significant, the grain size has to be very small, in few nanometers. So, if the grain size is in few nanometers, again even at higher temperature the grain boundary diffusion may dominate. So, if we plot the effective diffusion coefficient or the log of effective diffusion coefficient against the inverse temperature, we will get the plot similar to the dashed line which is shown here. So, we can see these plots are bound by lattice diffusivity on the lower side and the grain boundary diffusivity on the higher side. We can see at lower temperature, since the grain boundary diffusion is faster, the plot is almost parallel to the Arrhenius plot for grain boundary diffusion. At higher temperature, the plot almost coincides with the plot for lattice diffusion, and in between there is a transition. So, that is why the plot is curved in between. We can apply a similar treatment to pipe diffusion to find out the effective diffusion coefficient. I have shown a schematic here for the pipe diffusion. A dislocation can be considered as a pipe with a cross sectional area of, let us say, pi a square by 4, where a is the diameter of the pipe, and so the D effective again would be given by Hart's equation as f times dP plus D, where dP is the pipe diffusivity and D is the lattice diffusivity. For well annealed sample, f is approximately 10 to power minus 7, and now we can see for the pipe diffusion to be significant, that is for the pipe diffusion term to give at least 10% contribution to the effective diffusion term, dP has to be at least 10 to power 6 times the value of D, that is diffusivity. Now, this can show that at lower temperature grain boundary diffusion would dominate, but for pipe diffusion to dominate the temperature has to be even still further lower, unless the dislocation density is very high, which happens typically in heavily cold worked sample. So, in heavily cold worked sample the pipe diffusion may dominate at lower temperature. If we try to heat the sample, obviously there will be recovery and recrystallization occurring, and so the dislocation density will reduce, and again the contribution from pipe diffusion will come down. Obviously, at higher temperature again the lattice diffusion also starts dominating. Now, let us consider a couple of examples how the short circuit diffusion path can affect some practical examples. So, first consider a tracer experiment in which we determine the diffusivity of B in A. If you remember, we have studied this, how to measure the tracer diffusivity using radioactive isotopes. So, a similar geometry I have shown here. There is a tracer of B deposited on A. the instantaneous source of tracers exhibit diffusion on lateral surfaces in addition to the normal lattice diffusion. So, obviously, B star or the tracer of B will diffuse perpendicular to the surface inside this A, but towards the edges there will also be a surface diffusion on the surface obviously, and the surface diffusion is faster, and from surface there will also be a leakage current inside this material A. And so, at the surface there will be a 3-dimensional or at least 2-dimensional diffusion case, whereas the solution that we use getting the tracer diffusivities is a 1-dimensional diffusion solution. And so, when we try to analyze this tracer diffusion, we have to take care that the edge effects are eliminated. How do we do that? Obviously, there will be surfaces present and there will be surface diffusion and leakage occurring at the surface, and that is why we need to get rid of layer up to a few micron depths from both the surfaces, so that these 3D diffusion regions are avoided. At the center there will be a perfectly 1-dimensional diffusion case. So, we have to do all the analysis only at the central portion. So, I have shown the typical diffusion profile that would look in a tracer diffused sample here. So, this is the desired part exhibiting only lattice diffusion, which is at the center, and towards the edges the profiles are modified by the leakage from lateral surfaces. And so, before we analyze further, we have to cut the two surfaces. Similarly, this grain boundary diffusion or pipe diffusion may become problem in service in certain devices and systems. For example, in semiconductor devices, diffusion barriers are used between copper interconnects to prevent short circuiting. So, I have shown a schematic here. So, there are two copper interconnects which are separated by this diffusion barrier denoted as dB here. The diffusion barriers are typically the materials with very slow lattice diffusivities, and they are deposited as thin layers or thin films. However, at low operating temperatures typical of devices, the grain boundaries and dislocations present in the diffusion barrier thin films can cause short circuiting due to the faster diffusion along these defects. For example, if there are grain boundaries present inside the diffusion barrier, since the diffusivity along grain boundary is much faster and the structures usually operate at very low temperature, and so there will be diffusion of copper along the grain boundary, and thus it will cause short circuiting. Similarly, there may be the dislocation present inside this diffusion barrier, which will also act as short circuit diffusion path, leading to short circuiting and the subsequent failure of the device. So, we saw the fast diffusivity path or the short circuit diffusivity path today. We saw the simple model of Hart's equation, and also we saw how practically they are important. In the next class, we will analyze the diffusion along grain boundary in little more details. Thank you.